Hi, folks. Last set of lectures for the semester. Can you believe it? So we're going to jam out a little bit. All right, so I'm going to review some basic information from Chapter 2, getting into this Chapter 19, and then we'll start getting into the new stuff here, okay? But first, I want to just listen to this for like 20 more seconds, 10 more seconds. Okay, I suppose we gotta turn that off. Okay, let's get into it. So, a little bit of review of Chapter 2, because we're going to take a deep dive into the nucleus. Okay, and oftentimes in chemistry, we rarely talk about the nucleus because chemistry is done via the electrons. Okay, all the same, let's talk about the nucleus. Okay, so hopefully you remember this from your Chapter 2 from Chem 109, but as it were, atoms are mostly empty space. Okay, so there was some really clever experiments done, namely the Rutherford Experiment, right, where he fired alpha particles at thin gold films and found that most of them passed right through, but occasionally one would reflect right back. Okay, and this was described as like the equivalent of shooting like a missile at a piece of paper and the missile like flying back at you. Okay, and so the discovery there was that atoms are mostly empty space, and nearly all of the mass is in the nucleus. Okay, so if we think about our symbols here, this is going to help us a lot. We're going to use this type of nomenclature heavily in this chapter. So we remember, this would be our atomic symbol, okay, given from the periodic table. The superscript on the top left is the mass number. And so that's the number of protons plus neutrons. And it's called the mass number because the majority of the mass of an atom is in its protons and neutrons. And if we look at those masses, right here, a neutron, tiny, right, 1.67 times 10 to the minus 27. A proton, very similar. But now if you look at the mass of an electron, right, that's 10 to the minus 31. That's 10,000 times less massive. So nearly all of the mass is in the nucleus. Okay? So this letter Z right here, that's the atomic number of protons. And recall, that's what makes an atom unique. So all of the atoms on the table are distinguished by their number of protons. And so I know the font on this is small, but right, hydrogen, number 1, 1 proton. Helium, number 2, 2 protons. Lithium, number 3, 3 protons, and so forth. Okay. So here I've got a couple different flavors of sodium, and recall these are known as isotopes, and isotopes contain different number of neutrons. So for example, if we have, that got cut off. That should be sodium 23 with an 11 right there. I'll write that bigger. Sodium 23, 11. So the 11 tells me 11 protons, okay? But now the 23 tells me that there's 11 protons and 12 neutrons, okay? So that number 11 tells me that there has to be 11 protons. So I could subtract 23 minus 11, and then I get 12 neutrons. Okay? I could also have sodium 24, and it still has 11 protons, but it has an extra neutron. Okay? And we even have sodium 22. I don't have that pictured on here, but there is a sodium 22, and that only contains 11 neutrons. The vast majority of sodium is sodium 23. And some very small amounts of it are sodium 22 and sodium 24. And we know the vast majority of sodium is sodium 23 because if I were to zoom in on the mass of sodium right there, its average mass is something like 22.99 something. Okay, So because that number is very close to 23, that tells us sodium 23 is the most common. So let's take a look at some of these symbols that maybe aren't as familiar for us. And we're going to use all of these in this chapter. So for example, we could use this same type of symbology to write down the symbol of a neutron. Okay, and so we use a lowercase n. So we know neutrons don't have any protons, so that's why there's a 0 right there. And a neutron only is one neutron, so it's got a number 1. So 1, 0, n, that's our symbol for a neutron, and I want you to know that. So proton, we could write it as 1, 1p or 1, 1h, like hydrogen, right? We know that hydrogen, and hydrogen ion specifically, is a proton. And so once again, that 1 and 1 is because there's one proton and one proton, so 1, 1p. Okay. So the symbol becomes a little bit different with an electron. And technically, we call an electron a beta particle in this kind of radioactivity genre. And so we could write that in a couple different ways. So we notice that there's a 0 right there because it doesn't have a proton or a neutron. But we write -1 right there just so that we know that we're talking about an electron. And we could write that as 0, -1 beta, or 0, -1 e. Okay. So another type of isotope. So this is a hydrogen isotope known as deuterium, would be the full atom, right, containing an electron, a proton, and a neutron. But the deuteron would be what we call a heavy proton. Okay, so it's a proton that contains one neutron and one proton. So that's what makes it a deuteron. And so we could call that 21D, or sometimes that's written as 21H. Either one of those is okay. So we have alpha particles. An alpha particle is a helium nucleus. Okay, so notice here 4,2 alpha or even 4,2 helium. So that means it has 2 protons, right? And helium is number 2 right there. But now we recognize that it contains 2 neutrons, right? 2 plus 2 gives me 4. So 4,2 helium or 4,2 alpha, that's an alpha particle. And you can see its mass right there. It's quite heavy. And then finally, we have a positron, which we could think of as an anti-electron. Okay, so this is kind of weird stuff, weird particle physics stuff. And we'll see a few examples of positron chemistry. And so that's 0, +1 beta. Okay. So this stuff that we talked about here, all the symbols of these fundamental small nuclei, so that's fairly new. But this discussion of mass number, atomic number, and isotopes, that's good review. And so if you need a little bit more review, I would take a peek at chapter 2. Okay, in the next video, I'm going to get into the new material.